Great. Hi, everybody. How you doing so far? You doing all right? Listen, I know you just had a nice, tasty lunch, I hope, so I hope you're not too tired, because we got some really nice talks here for you. So if you're tired, you better wake up. So, all right, this next session, very special session, is about food and energy sector impacts and adaptation. So we'll have 15 minutes to talk. Speakers, please be very mindful of the timing, because we want to give everybody a chance to speak. The first speaker we'll have, and sorry if I pronounce anybody's name wrong, is Nathan Mueller.
Thanks, Veeshan. Hopefully after lunch is a good time to start talking about food if you're not too sleepy. I'm going to talk about the impacts of extreme heat on agriculture, and I sort of took my task in a sort of broad sense here to talk about multiple different aspects of agriculture. So I want to talk about rain-fed crops, irrigated crops, a bit about livestock, focusing on dairy, and then also about how agriculture is important for climate, in addition to how climate is important for agriculture. All right, so focusing on crops first. So we've known for a long time that extreme heat is bad for crops. I know Jonas will be talking about process-based models here shortly, so I'm going to focus just a little bit on statistical models that are widely used in literature. Some of you may have seen this graph before, coming from Schlenker and Roberts' 2009 paper, very famous paper in this field, showing that basically the increased exposure to high temperatures, kind of above 30 degrees C or so, are associated with pretty profound yield reductions. And so these extremely hot temperatures really control a lot of projected yield losses, and then these sorts of models get used to project all sorts of different outcomes that are related to agriculture, including agricultural GDP or poverty, things like that. And there are limitations to these sorts of models from a sort of process understanding perspective, but they're still very useful and widely used. So why do we see this sort of association? There are a lot of different mechanisms for why heat is important for crops. For one, high temperatures lead to faster crop development, so they hasten the time to maturity, and then that can lead to lower yields. They can directly alter rates of photosynthesis, respiration, and grain filling. Temperature also really matters for water stress, so higher temperature, more VPD, that can stress crops directly, but also means more water loss from the soil, and then you have soil moisture stress. You can have direct cellular damage, but only at really high temperatures. Heat can also affect pests and diseases. And then another really important one is changes to irrigation water supplies. So I'm going to focus on 3 and 6 here. First, when we think about temperature impacts on water stress, we can go into thinking about that problem from a little bit more of the plant's perspective. So what the plant really cares about is how much water does it have access to and how much water is being demanded by the atmosphere, right? And so we can imagine that basically an optimal day might be somewhere in the middle there, but as you have a very high soil water and low evaporative demand, you're going to get waterlogging conditions, and we might expect low yields to be associated with that. Or conversely, high evaporative demand and low soil moisture, the atmosphere is pulling a lot of water, but there's not a lot of water available, and that's going to stress the plant. So that was our framework, and we set about to test this, and by we, I really mean Kyung Choi over there, and parameterized a statistical model that looked at this framework. And so you can see here, these outlined boxes basically represent the worst 15% of growing season conditions, and they really do correspond with those two extremes of kind of dry air, dry soil, and and wet soil and low evaporative demand. And then using these definitions, we can actually go back and attribute historical crop losses to these extreme conditions, and we can see how much yields were reduced in any given year relative to a counterfactual where those conditions were not experienced. And so you can see here for maize, for rain-fed maize, these hot and dry conditions are really responsible for the majority of the yield losses, but also waterlogging is quite important in many years as well. All right, so this is for rain-fed crops, but what about for irrigated crops? So irrigated crops are much less sensitive to high temperatures and high VPD because they just have water, soil moisture artificially supplied to them. But they are really vulnerable to the sustainability of water supplies under warming. And so this is just one example of a study where we looked at that. This is for the San Joaquin Basin in California. The bars here represent water consumption. It's kind of a climatology in every month. And this is all surface water consumption, not groundwater. And then this is rainfall runoff and snowmelt runoff under historical conditions and projected future conditions. And so we know that this surface water consumption is being supplied somehow, right? Even if there isn't runoff happening simultaneously in that month. So either through reservoir storage or interbasin transfers. But as we move to the future and we get a lot more rainfall runoff when we don't want it and a lot less snowmelt runoff when we do want it, that's going to place pressure on those systems. So basically, snowmelt here is acting as a natural reservoir and providing irrigation water supplies farther into the growing season. And that kind of service is going to be reduced in the future. And so we can see here in this map all of the basins around the world, basically where the gray in that previous plot is projected to increase and snowmelt is projected to decrease. All right, so that was a bit about crops. Now let's talk about livestock. So, just like humans, livestock are sensitive to high temperatures. You get increased stress responses, hormones, heart rate, respiration rate, metabolism, and appetite can all be affected. And basically what we've done is we've looked at this in dairy systems, and the net result is extreme heat means lower yields. And so to do this, we took kind of a Schlenker and Roberts style approach where we looked at exposure to THI, which is not one of the heat indices that has been mentioned so far, but this is really the dominant heat index used in animal science literature, the temperature and humidity index. And we looked at monthly state-level milk yield records, and then we know, based on Census of Agriculture, where the cows are located within each state, within those states, and then we know the daily distribution of weather that those cows are exposed to. So basically, we take that exposure and we relate it to the yields, and we can see very clearly both the cold stress and heat stress response. And something that's really interesting is the farther back in time we looked, the more sensitive the system was, but in more recent years, it is less sensitive, indicating reduction in vulnerability of the sector through kind of more housing, more intensive management practices. All right, so this is using THI, as I mentioned, but THI is a really kind of old school construct it's been around, but not really re-examined much. And so just wanted to give a shout out to Kyung's poster this afternoon where we're using machine learning and a different data set of milk yields to basically try and tease apart the relationships, including with extreme values between milk yield and some of these individual variables to see if we can try and come up with something that performs better than THI. All right, so all this motivates really thinking about how extremes are changing in agricultural regions. And so this is some work that I did some years ago now, but we were really interested in how these extremes were changing and identified quantile regression as a useful tool to look at that. So here, if we go to the heart of the Corn Belt in Story County, Iowa, each of these clouds of points represents the distribution of daily maximum temperatures in a given year over the summer months. And then we can fit quantile regression to that. And so something surprising popped out. You know, these are regions, and it's been mentioned previously in this workshop, but these are regions where extreme temperatures have actually gone down, kind of surprisingly. So we asked, you know, is this just the Dust Bowl? Is it just, you know, aerosol forcing in the 70s? And tried to slice and dice it a whole bunch of different ways. Even if you remove the influence of those things, you do see this cooling right over the Corn Belt, which is pretty interesting. And you do have some irrigation here and some irrigation in here. But I want to emphasize that most of the agriculture in the Midwest is rain-fed. And so these are raw station data, so there's some, you know, caveats to interpreting the absolute magnitude of the trends, but I think it's important the spatial pattern of them really demonstrate this kind of this warming hole phenomenon that's been discussed. Now, what's unique about this area is that it actually does have the peak productivity of anywhere on the planet. So we have vast area that's agricultural. These are very pampered plants that have lots of nutrients supplied, very protected from pests and diseases, and have been bred for high productivity. And so that involves fixing a lot of carbon and doing a lot of gas exchange, right? So that led to our hypothesis that maybe the low intensity of agriculture of 50, 70, 100 years ago is quite distinct from the land use characteristics of contemporary agriculture, and maybe that had something to do with this. And agronomists have known for a long time that rates of evapotranspiration are really dependent upon management and not just irrigation, but also nitrogen supply. So, but there's kind of this disconnect between this field level work and kind of thinking about the climate implications. So we decided to test that a little bit. First of all, spatially looking at basically where has agriculture intensified and what are the extreme temperature trends in those regions. And you can see that as you get to higher growth and productivity, you have lower and lower extreme temperature trends. We also tested this idea that it's a moisture mechanism by comparing irrigated and rain-fed areas. So this is for irrigated areas. These are the temperature trends for irrigated areas, basically in drought conditions and in non-drought conditions. So we can see that because we're supplying water to these regions, that cooling basically continues. Whereas if you look at the rain-fed areas, you see cooling rates that are similar to the irrigated areas, but only if there's sufficient soil moisture, right? So then it just pops right back up to where it would have been otherwise. So we think this is that agriculture is probably a contributor to this Midwest summer warming hole. We have also examined precipitation and some other explanations, and this held up pretty well, but you know, I imagine there probably could very well be multiple contributions to this phenomenon. And I think a big question is, you know, will it persist into the future? And I want to give a shout out to Marian Shea, who's also presenting a poster where we're using CSM to test some idealized cropland intensification scenarios and look at the sensitivity of surface temperature to those and heat extremes. Right? So in conclusion, lots of different mechanisms here. High temps are associated with pretty dramatic rain-fed crop yield losses due to this dry atmosphere and dry soil phenomenon. Also places irrigation water supplies at risk and is important for thinking about livestock as well. Though high temps have been increasing in a lot of areas, I think our agriculture, at least in the Midwest US, has been pretty lucky so far, and possibly that agriculture itself has contributed to this. So thanks.
All right, we got time for one quick question if anyone has one. No? Okay, well, thanks for that, Fat. Actually, I got a question for you, since you guys. So, what do you think? So, I have a friend. She's from Trinidad, and she's been working on, I guess, breeding heat-adapted cocoa because that's a big crop over there. What do you think about these efforts where they're trying to make more heat-resilient plants? Do you think it's a promising adaptation thing?
Yeah, I think it's huge. And sometimes the breeding just happens and they put out different cultivars and say these ones are more successful, and we don't always know why physiologically they're more successful. But one important mechanism that is in some crops is that they'll be more sensitive to high VPD and close their stomates and try and preserve some soil water, and that can sometimes buy them some important time. So, yeah.
Okay, thank you for that nice talk. The next speaker is going to be Jonas Jaegermeyr.
Hi, everybody. Thanks for having me. I'm Jonas Jaegermeyr. I'm actually based out of New York. I'm with Radley and a bunch of other folks at Columbia and NASA GIS. And what we're doing is we're leveraging process-based crop models. So this is a perfect follow-up to what Nathan showed us. Now, I would like to share some insights what these mechanistic models point to and how these long-term projections could look like. Great. So I don't have the striking slide on extreme heat. What I was planning to do is give a general overview of what the field is showing, what these models are indicating and then highlight a current attribution study that we're doing that looks at heat waves. And in general, mentioning process-based models. So we're leveraging a whole ensemble. We're creating a multi-model ensemble trying to harmonize and formalize the impacts sector a little bit. Pretty much what the climate community did with CMIT. We're lagging behind a decade or two, but we're trying to standardize things a little bit. So we're not just using one model and apply that and say, this is how the future is going to look like. We're trying to harmonize the protocol and say, you all use your model, you run it in your institute, but we work together using the same forcing data, using the same assumptions, using the same input data and protocols to then effectively get an idea about uncertainty. Because unfortunately, it's still the case that the uncertainty associated with impact models is by far larger than the uncertainty coming from the climate models. So there's a lot of homework to be done here, and these maps, animation of these maps that we just went through, highlight that. So you can see these stark differences between climate impacts under a high emission scenario for maize and for wheat. So it really matters what crop you grow and where you grow it. And it doesn't mean that wheat is not responding to high temperatures. Wheat yields also decline under increasing temperatures, but wheat, on the other hand, is very sensitive to higher CO2 concentrations. It's traditionally grown at higher latitudes, so it's a very complex feedback mechanism that we try to unpack. One of the main findings in climate change impacts in global agriculture that's not directly intuitive from these maps is that impacts are largest in lower latitudes. So the tropics, subtropical regions will see the brunt of climate impacts, and that's a problem because adaptation capacity in those regions is usually very low too. And that holds true for pretty much all crops we are studying. An interesting way to look at impacts is the time of climate impact emergence. So that's a metric that has been used in the climate sciences quite a bit, but not so much in the impact sciences. So we're trying to see when the average signal is leaving the envelope of historical variability or noise. And when we reach that point in time, we think of a new norm, where there's a fundamental change happening in the system. At global level, that historical envelope is pretty narrow, so you reach these times very early on. And this study shows that these point in time, in terms of climate impact emergence, basically occurs within the next decade under a high emission scenario, and mid-century for a high mitigation scenario. If you look at it from a global aggregation perspective and look at all the areas where maize is currently grown, you can sum up these areas that get to such a point of climate impact emergence, the red line with a circled 74%, highlighting that 3 out of 4, 3/4 of the total global maize cultivated areas are indicated to see such fundamental changes. There's a lot of detail in here. The differences to earlier studies indicated by GGCMI CMIP5, which I'm happy to talk about, why CMIP6 shows so much of a stronger signal. And it's not just the hot model problem or a generally warmer CMIP6. It's really an advancement in the impact sciences that the models have advanced. But that's a separate discussion. I'm happy to elaborate a little bit. So for wheat, on the other side, we are actually talking about an emergence of a positive change. But it's important to realize that these changes often level off. So we have a peak and decline scenario. And towards the end of the century, there's huge uncertainty across these impact models. That's indicated by the shading, yellow shading. Some models indicate substantial declines. Others still continue to see strong sensitivities to increasing CO2 concentrations. And when you look to the metrics of the climate sciences, the emergence times in temperature and precipitation, we see that we're generally on the same timeline. So those are figures from CMIP5, corroborating our findings that between the 2020s, 2030s for temperature, and for precipitation, that's the color bar. So the darker it is, the earlier these emergences occur, is basically in the same ballpark of findings. Going back to the global maps, there are regions of there will be winners and losers, and the map is really difficult to unpack. But the general patterns are clear that maize is largely seeing declines in lower latitudes, especially, but even wheat has areas with declines. Only talking about maize and wheat is obviously not enough. Those are the big staple crops that we focus on, but it's really time to move on. So in a current project, we're trying to do that, push the frontier of crop modeling, which is difficult to do because we don't have the data, the models, the time, the funding. But we do try to add additional crops to the list. And in this project, we have actually a bunch, 18 different additional crops that we speak of opportunity crops that we try to evaluate, and we're able to make beautiful animations. This is actually an interactive map that you can go on and play around and look at the different nutritional components and climate impacts. And this is the way to go. It's a very simplistic model, though, so this needs to be underpinned by additional modeling support to corroborate the findings. But long-term impacts is only one thing. It's really important to realize that interannual changes can be substantial, even though yields over a period of 30 years can go up or go down. And this is what the models indicate as well. So the coefficient of variation, CV, is increasing for pretty much every crop we're studying, meaning that the fluctuations, the difference between a good year and a bad year, increases over time. In areas where we see wheat yields with potential gains, we also see that these amplitudes are increasing, which is also a reason for concern because it can destabilize a system, even though your average yields may actually mask or hide some of these effects. This, however, is a good segue to talking more about extremes, because that's basically driving these interannual changes. And we're interested in heat waves and droughts. Floods as well, it's a big driver of crop yield changes, as Nathan also pointed out. But the process-based crop models are actually really bad at responding to flooding and waterlogging. So this is something we're currently working on. So let's focus on heat waves and droughts for now. We know that the frequency is expected to increase and the severity as well. It's especially for heat waves, as you put it in these box plot figures for an attribution component, that there are significant changes between a control or a PI control run and even a low emission climate change or high mitigation climate change scenario. Now the question is, how does that impact crop yields? And there's some evidence from the literature. Here's a seminal paper by Corey Lesk, who was also in our group, looking at reported yields over time, finding that this is a little bit of a complicated composite figure, but it basically overlays all the historical extreme events recorded as droughts and heat waves in a disaster database. And if you group them by early events and later events, now here in this case happening after 1985, the impacts increased. A PhD student of mine did the same study for Europe, focusing on different crops and different events, but basically finding the same signal, that more recent events seem to have larger impacts, actually tripling the impacts on cereals in Europe, which is a concern, and then leads to the question, okay, how do we extrapolate that to the future? Which is something we're currently working on. I don't have the results right here yet. I want to stick with that historical attribution for a second. This is an ongoing project where we use crop modeling to understand that signal a little bit. And first thing is we kind of reproduce these observational data. We're grouping droughts and heat waves for events happening before 1990 and after. And we indeed find the same thing. The lighter green shows the previous events, and the bolder line, the darker green, the later events. And impacts do seem to increase over time. Now the question is that a climate signal, or are there other factors at play that can actually come in here too? And this is the attribution work we're currently doing with it's called the Atrici counterfactual. So that's actually a reanalysis counterfactual, so you can actually do event attribution, not just a climate simulation attribution. And first looking at observations in gray and the simulations in green, the models do a fairly good job at reproducing the observed impacts. And in a world where you remove anthropogenic forcing, the impacts of heat waves are substantially reduced. So that's good, and that's basically in line with the time trend we saw. So much of the time trend in heat waves can be attributed to anthropogenic climate change. For droughts, however, the picture is very messy, and we can't conclude with the same story. The models don't perfectly reproduce the observational data, but also there's very little difference between a factual and a counterfactual simulation. The interpretation here is that there are additional factors that explain that. The models are imperfect, but also the way we report disasters in the first place has changed over time. So there's a lot to read into this, but in the next step, we're using the climate models to look out into the future and see how these extreme events may impact global agriculture forward. In conclusion, fairly generic at this point, the latest generation of models show that impacts actually seem to be happening earlier, and the climate signal is stronger than expected. Adverse impacts are expected at lower latitudes, disproportionately affecting lower income countries with lower adaptation capacity. Increasing interannual variability is a concern and can actually destabilize the food system. And then with a focus on extreme events, we can attribute the heat waves to anthropogenic climate change, but for droughts, the picture is more complex, at least in the impact studies we're conducting here. Thanks.
Thanks, Jonas. Chris Callahan from Stanford. I was curious about the mechanism for the interannual variability change, and in particular, whether that was just changing in climate variability driving crop changes, or there was something mechanistic or physiological at the crop level that might amplify climatic changes and sort of propagate through into interannual variability change in yields.
Good question. Let's see if I understood it correctly. So I didn't mention, but everything management is kept constant throughout these whole simulation protocols because we want to isolate the climate signal. So fertilizer applications, planting dates, crop land allocations, all that is kept constant. So everything we see is a climate signal. But then, of course, it's a process-based model. So you will have nonlinear feedbacks, reaching certain biological thresholds. Plant may die, and then you have higher soil evaporation, all these kind of things. I'm not sure if that, yeah.
We'll take one more quick one.
Hi, I'm Michelle from the Bergen County Academies High School, and my question was related to the projections about maize and wheat. So on that slide, I was just wondering if you could explain a bit more on what you think will happen to the wheat eventually. Do you think that the projections will eventually catch up to the maize, or does it exhibit similar patterns to the maize, or just in a slower manner, or are the characteristics of it completely different that they will exhibit different patterns towards the end of the century?
Right. No, good question. They are fundamentally different. Much to the point that wheat is very sensitive to CO2 changes, atmospheric CO2 concentrations, and maize as a C4 crop isn't. So maize can't benefit from a higher CO2 concentration, which for wheat increases your water use efficiency and your photosynthesis activity, helps with phenological development. But it's one of the highest uncertainties in the models. So there are some models that are very, have a conservative approach to CO2, and others just go through the roof, whatever. So this is one of the biggest fields of where we need to look closer. It's not that these values are unrealistic. They're all in line with what field experiments show. The question is, can you realize those very high amplification levels globally across agroecosystems in nutrient stress environments and water stress, so there's a lot of ifs related to that. The other thing I will say is that the wheat projections, in my eyes, are very optimistic still. There are a lot of blind spots that the models can't really respond to, as I mentioned, floods, but heat stress, direct heat impact on, Nathan mentioned at the cellular level, is something the models can't really respond to, and much what they see is actually water stress. So a leaf temperature affecting the tissue damage is something the models don't really do well. So thanks.
All right. So next person we got is Luke Parsons.
Hi, everyone. Yeah, my name is Luke Parsons. I'm a climate scientist at the Nature Conservancy. And today I'm going to be talking more about the heat impacts of potential labor productivity of outdoor workers. So if you don't really understand much about this topic yet, if you haven't studied it, I'll try to orient you. First of all, I'm going to be talking about what type of metric we use, wet bulb globe temperature, which I think folks have mentioned before. And then I'm going to get into more about how we relate humid heat to how hard people are working outside, and then how much their labor could slow down. And then to look at where around the world maybe we should see where it's risky for labor losses, I'm going to apply this IPCC AR5, AR6 framework. We're going to look at where it's hot and humid. Then we'll look at where there's people of working age. And then we'll also look at maybe who's vulnerable, who has to work outside, who has less adaptive capacity. And if you want to tune out for just a minute, what I'll show you is that there's considerable uncertainty here, like with some of the other modeling, in how exactly we assume people are responding to humid heat when they're working outside. But despite this, because it's so hot and humid in some areas where people have to work outside, listed here, there are some areas that are definitely at higher risk, regardless of how we try to model this. So outside your body, not only does it matter how breathable your clothing is, but it also matters how hot and humid it is. So we're going to use this metric, wet bulb globe temperature, that includes temperature, humidity, wind speed, and sun exposure. This is used in military, occupational health, and athletic events to determine outside, let's say, based on how hot and humid it is, if it's safe to do heavy labor or if it's safe to exercise intensely. Usually this is measured with some sort of expensive device or sensor pictured here in the lower right. We don't have those all around the globe typically. So instead what we'll do is we'll estimate this from weather station, weather, and climate model data. And specifically thanks to Dr. Chin Kong, who's actually here today, for sharing your data. They're sharing the wet bulb globe temperature with me that I'll be using. We use 3 hourly average estimates of wet bulb globe temperature from reanalysis or ERA5 data going back to about 1950. Then for that first 25 years, we use that to bias correct CMIP6 models that have 3 hourly data that we use to calculate wet bulb globe temperature. And then we use the historical runs up till the present, and then moving forward from 2015 to mid-century, we're going to use SSP3, a moderately high emissions scenario, to look at future impacts. So that was outside the body, wet bulb globe temperature. Inside the body, I'm not going to talk a lot about this, but it really matters how old you are, your health status. Do you have a heart condition, for example? If you're taking a medication that inhibits your ability to sweat, are you acclimatized to the heat? But I'll focus mostly today on intensity of work. We're going to look at mostly people who have to work outside in the agricultural industry. Usually they're generating some sort of power as they're working, right? They generate internal body heat. Usually you're talking about somebody who's digging a trench or lifting like a heavy bushel of vegetables. For context here, a typical toaster, as pictured here, might use 800 watts of power. So think if you're working intensely outside in the heat, your body might be generating half a toaster worth of energy, right? So you have to be able to dissipate that to the outside environment via evaporative cooling of sweat, which can be really hard to do if it's too hot and humid. So you naturally slow the pace of your work or you have some serious health consequences. All right, so then how are we going to relate how hot and humid it is to how much labor could be lost around the globe or safe labor hours lost? One way we could go about doing this is using the method of NIOSH in North America, or the International Organization on Standardization. They suggest work-rest cycles as a function of what you're wearing, how acclimatized you are, how hot and humid it is, to keep core temperatures at a safe level. Usually this is below 38 C. Some various folks have fit exposure response functions from the work rest cycles as a function of wet bulb globe temperature to then look all around the globe. Where is it hot and humid? How much safe labor time could be lost? These are listed here. This is not all inclusive. There's another method then, commonly used, I'll call Kellstrom throughout the rest of my talk. This is by Sahu, Set, and Kellstrom. They looked at Indian rice workers and also an older study of African miners and looked at how they slowed their labor down, labor productivity, kind of self-paced, as a function of heat and humidity. This has been used really commonly. If you ever read the Lancet Countdown on Health and Climate Change, this is the method, the exposure response function they use. There's this recent one led by Foster et al. This is a lab-controlled chamber experiment, which I think is interesting. So they take young, healthy, unacclimatized, fit college students, and they put them on exercise bikes, for example, measure their core temperature, and look at how quickly they slow down their labor as a function of heat and humidity compared to if it's cool in the chamber. This method's been used also. So you can look, if you're interested in this, there's this great review paper that I'm going to point you to here at the bottom. All right, now to help visualize this, because there's a lot of words, let's look at labor capacity slowdowns per hour as a function of wet bulb globe temperature on the x-axis. So if we use that lab-controlled study, here's the blue line, so you'll see above about 15 to 20 degrees, this is where we start seeing work capacity losses as a function of heat and humidity that continue to increase up to above, let's say, 80% at 40 degrees C in wet bulb globe temperature. Then let's look at the ISO safety recommendations Basically, they say, oh, you can do heavy manual labor for an acclimatized worker in light clothing outside up until about 26 degrees, then you have these really strongly suggested work rest cycles until you get up to about 33, and then they say stop working. That's going to be kind of dangerous. You're going to have severe heat stress or illness. And then if you look at the Sahu study of Kellstrom et al. 2018, you kind of fall somewhere in the middle. Notice above 25, 26, that's where we start losing labor. So clearly different approaches are going to give us different absolute answers, like how many potential billions of hours of labor loss could happen per year around the globe if we add it up. We're going to probably have some wildly different answers based on these different exposure response functions. But does it really matter for targeting like which regions are at the highest risk? So again, to assess this, I'm going to be using reanalysis data and CMIP6 data to look where it's hot and humid now and in the future, working age population data from GPW version 4 2020 data, and then we'll use ILO and World Bank data to look within each country what fraction of the working age population works outside in ag, forestry, and fisheries. So first, let's zoom in on where it's hot and humid. Most folks, I think, have focused a lot on North America and Europe so far. We've had a few global talks, but here we're going to look at the average 99th percentile over the last 20 years of wet bulb globe temperature. I've picked very kind of craftily here my color bar. It's divergent. It shouldn't do that, but what I did here was yellow is 26 degrees. That's where we start seeing labor work rest cycle recommendations from ISO. And then when we get up to 33, that's that deep red where we saturate the color bar. That's where we get to like 100% rest for somebody outside who's acclimatized, working according to the ISO heavy manual labor. So you'll start seeing there are certain places that are deep red on this map as we look around into the tropics and mid-latitudes, right? Some places are regularly hitting this 33-degree wet bulb globe temperature threshold. So that was just the 99th percentile. Let's now look at every kind of 3-hour time period throughout the day, relate this to how much potential labor loss could be kind of lost around the globe. So what I'm going to do is I'm going to look at data from 7 a.m. to 7 p.m. local time. Let's look at how hot and humid it is on average every hour of that day. Then I relate it to those 3 exposure response functions and look at how much potential labor could be lost 365 days total out of the year if someone wanted to go work outside. So for example, here I'm showing you the Kellstrom Sahu rice worker method. This is percent of hours per person per year. I wanted to show some detail at the lower end, so it's a log scale. It goes up to about 40%. Notice the deep red across the tropics. Then if we look at that lab-controlled exposure response function, notice we start getting losses above 15, 16 degrees. So notice the yellow starts creeping up into higher latitudes, but still deep red in the tropics where it's hot. And if we use the ISO guidelines, they say there's not going to be any labor loss until you get up to 26. But once you get up to 26 degrees, they say that you're really up on that labor loss curve, and it steeply says there's going to be losses of safe work hours. So it's really, really red, or lots of safe work time lost around the deep tropics. So it might be hard to see what I'm showing here, so I'm just going to show you a latitudinal average. So on the x-axis is latitude, y-axis is percent of hours lost per person per year. So the Foster is shown in blue, the ISO is shown in red, and the Kellstrom method is shown here in gray. This is just averages over land. So you could see with the ILO right next to the equator, maybe you would, or with the Foster method, you might see as high as 20% losses on average over land. With the Kellstrom method, it might be as low as 12%, right? But the places typically that pop out as having the highest losses associated with humid heat are pretty similar regardless of what method we pick here, even if the absolute numbers are really wildly different. So far, I've been agnostic or haven't overlaid any working age population data, so let's go ahead and do that next. So let's take the average labor losses across these 3 exposure response functions. Then let's overlay working age population data within each country, and then I'm just going to put on a map here what's the average current country level population weighted labor losses potentially for that 12-hour workday. So here the color bar goes up to about 25% where it saturates out at yellow. So you'll notice that there's these areas that are kind of this pink color, like in sub-Saharan Africa, 10 to 15%. Places like Southeast Asia are in the 25% range. So I can actually put your eyes on some slightly more quantifiable numbers instead of the color bar here. I'm just going to show you the countries with the 10 greatest losses on average. On the x-axis and the y-axis is population-weighted annual labor losses for heavy labor within these countries. So, for example, Cambodia is our I don't say this joking, I guess, biggest loser. maybe as low as 18%, as high as 30% there, depending on what method we pick. But the point here is that the kind of order of these more or less, as we work down for the countries with the 10 greatest losses, that it doesn't really matter the way that you pick to do this. The countries that are at highest risk are at highest risk, typically Southeast to South Asia, Sub-Saharan Africa, tropical Northern South America with Suriname there. So then finally, let's get to where are there people who kind of have to work outside probably. They can try to move this labor to the nighttime, but oftentimes people have to be outside during the day harvesting vegetables, for example. So let's look at again, annual labor losses, the population data, and then also now let's use our ILO and World Bank data to look at the fraction of the working age population that works in agriculture, forestry, and fisheries industries, where you usually have to be outside doing relatively intense work. Thank you. So notice Sub-Saharan Africa, we're looking at 60, 70% of some of these countries have people working outside. India is closer to 40%. So now if we just multiply all these out, percent of people in the working age population having to work outside times the annual labor losses, now we have this log scale here. You'll see that immediately India pops out. If we have a couple hundred billion potential labor loss hours per year, followed by China, just because these are big countries with lots of people, followed by places like Indonesia. Even though Cambodia, on average per person, might have more losses, but when you add in population, this is what you get. Briefly, let's just go into mid-century multi-model mean projected labor losses. This is going to look really similar to a map I showed you for a current time period, but you're just going to see a lot more yellow and orange, just because this has jumped up for a lot of these countries, whereas before Cambodia might have like maxed out at 30% according to this ISO method. Now we're looking at closer to 40% of the hours are exceeding these safety thresholds according to the ISO. If you're using that Kelstrom method, it might be only 25% of the hours out of the year where you're not supposed to, where you like lose those hours because of humid heat. Again, the same countries tend to pop out here. Places I really worry about are areas in like tropical Indian Ocean and Pacific where we have massive increases in a number of hours that exceed these thresholds. So in summary here, our estimates can really, really vary depending on how we're going to assume workers are responding to human heat, or what are we saying is safe or not safe for them to work outside. Also, what's really important here is like, are people moving working hours? Like I work at the Nature Conservancy where we've gone in and interviewed people in Indonesia, for example, and they just stop working in the middle of the day and lay down in the shade sometimes or move work inside. We're not accounting for that here. Also, mechanization is not accounted for. Like if you don't have to go do heavy manual labor, you can get a machine to do it for you. This doesn't really count the way we're doing this. Despite these uncertainties though, we have really high risk areas here, as I'm illustrating on the maps that I showed you before, East, Southeast, South, and Southwest Asia, Northern tropical South America, Sub-Saharan Africa, and I didn't get into this very much today for lack of time, but I get really worried about tropical South America because we're looking at a lot of these countries, regardless of whose population projection you use, they're supposed to grow by 50 to 80% in population size by mid-century. You have a tremendous number of people who are then working outside and large fractions of the population that need to be out there with more people needing to be fed. So with that, I'll take questions. Thank you.
Quick question and quick answer.
Hopefully this can be quick. So many of the areas that you show in this map coincide with the areas that Jonas just showed us, where there's going to be a loss in like agricultural production of many crops. Yeah. So have you all thought about like the intersection of those two and sort of characterizing agricultural risks? Maybe thinking about the types of crops that are grown there and the feasibility of that intersecting.
I should say, I haven't personally looked into this. I can't recall it right off the top of my head. There are folks who've looked at the overlap of both the crop productivity and the labor productivity side. I have not personally done that. There is a study out there that's looked at that, though. That's very important to look into. Yeah. Thanks.
All right. Next person we got is Andrea Staid.
Okay, we have not heard very much about energy in the last 2 days, and I have a lot that I could talk about, and I will really try not to go over. So bear with me. I might go kind of quick through some of these concepts, but I'm really going to try to instill the basics for you all and then sort of breeze through some of the more detailed results that we have here. Okay, so what can extreme heat mean for the power system, right? So maybe the most obvious is increased electricity demand. When it gets really hot, everyone who has an air conditioner is going to turn it on. That uses more electricity, which means that the demand across an electric system, right, for a utility company is going to go up. We see plenty of examples of this in the media, and this is like one of the main indicators of grid stress when things get hot. Along with increased demand can often come high prices, right? So both high prices for individual consumers because they are using more electricity, and high prices for electricity at the market scale because you have to call on all available resources, and it gets really expensive to call on resources that are only meant to be run, a couple days a year. And so we have really high demand, and if you pick up on this, this might be happening so frequently that Reuters doesn't even bother to update their picture for their news alerts anymore. Okay, so we have demand, but there are other things that cause grid stress during extreme heat periods as well. So as I said, the market price gets high because you have all available generators online trying to produce enough power to serve customers. In case it's not obvious, you cannot build a new generator overnight when it gets really hot. So if we reach an amount of demand that the generators cannot supply, that's when people lose power, right? That's when we call on customers to reduce your air conditioner set temperature. In some cases, you do rolling blackouts to try to keep the load lower for the grid so that the generators can supply power to keep critical facilities online, critical loads online. So really, there's just a reduced margin for anything to go wrong, right? Things fail all the time, randomly, for all sorts of reasons, related to heat and not related to heat. But when you need everything on the system to be working well, you have no margin for failure. Okay, so at the same time that we have really high loads, you also have stress on assets. Generators operate at both reduced efficiencies and with reduced capacities when it gets really hot. This is, a physical phenomenon because of the cycles, right? The cycles of burning fuel that they go through. Transmission lines are a physical metal cable, and when they get really hot, they sag, and we can't allow them to sag so much that they hit trees, and so they have hard limits on how hot they can get, and so you have to reduce the amount of power that can flow through some of these lines when it gets really hot. You also, we've seen some examples of these really widespread heat events. If your neighbors are also really hot, then you can't import power when you need it, right? So we have an interconnected grid across most of the United States and most of the world, and it's extremely common to share power, right? We have these interconnected lines. You import power, you export power. If everyone is really hot and if everyone needs all available resources, then that is really constraining, and you might not be able to get what you expect from your neighbors. I should also say that, right, this is today, right? We know these things happen. We know the climate is going to get warmer, and so there are some real implications for what this all might mean going forward and what utility companies need to be thinking about when they're facing a question of planning for, 2040, 2050, 2060 conditions. So what it means to plan the power system, I will sort of say that, traditional long-term planning tries to balance supply and demand. I put it in a few words to make it look relatively simple. It's not, right? Like, planning for supply and demand comes with massive uncertainties on the demand side in terms of population growth, changes in technology. If we all get electric vehicles, that changes things quite a bit. If we have AI data centers popping up all over the world, these are massive uncertainties on the demand side. At the same time, we're really trying to decarbonize the supply side. So instead of building coal plants or gas plants, we're trying to meet this changing load with wind, with solar, with batteries, which also introduces more of a weather dependence, right? Wind and solar depend on the weather. You can't just turn them up or turn them down when you want to. Okay, so we already have all of these complexities that go into traditional grid planning. So I say traditional, not simple, not basic. It's just traditional how we've been dealing with it. If you take climate into that picture, then a lot of things start to change, right? So technology adoption, as I mentioned, people might get EVs. People might also buy air conditioners where they haven't had them before, right? The Pacific Northwest could certainly use some air conditioners this week. And there's not a high penetration of air conditioners in a lot of parts of the country that are now seeing heat. And so you have some technology option that will be climate driven. We have new climate norms and extremes, which we've heard a ton about, right? This science that you all have been talking about determines what that load picture does, right? It gets hot, it gets cold, load increases on both ends of that spectrum. We've also seen some really interesting, sort of new to us examples of load increasing before a major extreme event such as a hurricane because everyone charges their electric vehicles in case they need to evacuate. Right? So we have these like new lumpy loads that are coming onto the system that are driven by weather patterns. The shifts in peak demand, so maybe I should also go back and mention traditional long-term grid planning often looked at a summer peak load and a winter peak load and say, hey, if we can meet those, we'll be fine for everything in between. We are seeing already some shifts in peak load, and it might not be the single hottest day, it might be day 5 of a 7-day heat wave that's not the single hottest, but you just haven't had enough overnight cooling, right? We're seeing this increase in nighttime temperatures, which has a drastic increase in load. So anyway, there's a lot of complexity in terms of shifts in peak and when it's happening, and we might need to consider a lot more time periods other than just summer peak and winter peak when we're planning. I mentioned the supply. I also mentioned I'm trying to go quickly, which I am not. Okay, so I work for EPRI, which is the Electric Power Research Institute, and we have a 3-year initiative called Climate Ready, the Climate Resilience and Adaptation Initiative, that utility companies around the world are supporting, are members of, where we are really trying to dive into these questions of how climate can inform planning, and especially adaptation and what to do about the fact that, we might not be as resilient as we want to. So quick plug for Climate Ready. I will not talk too much about it, but within Climate Ready, we recognize that, this planning question encompasses many different modeling approaches for various computational reasons, for various industry reasons, and the climate picture is a strong motivator for the need for integrating these across the board so that you are tracking consistent assumptions for your climate risks and for how the grid is responding to those climate risks across a set of tools. So I won't get into these tools. Again, I don't have time, but look up Climate Ready. There's a lot of great information out there. But a little bit of motivation for sort of this reasons for including climate data in a really meaningful way. This is a lot of information, but if you look at the left-hand slide, these are bar plots of demand, of electricity demand for a case study system across historical years. So this is really just showing you the impact of natural variability, right? Our peak load varies year to year. This is for a synthetic grid representing Texas, so Texas climate, Texas synthetic grid. On the low end, it's relatively consistent across these years, but the peak load varies drastically from year to year. If you move to 2050, and this is moving to 2050 without climate change, but with the inclusions of changes in demand, right? So changes in population, changes in technologies, you start to see a winter peak arise in Texas, right? So summer is no longer the driver, winter's the driver, and yet we still have this massive variability year to year. A lot of people want to use a typical meteorological year. This is really easy for planning in many cases. A typical meteorological year is going to miss these peaks completely. If we do add in the warming signal, right, so on the right-hand side, we take 2050 with 2050 climate under an SSP 7.0 scenario, your winter peak is reduced, right? It's warmer, so there's less need for heating in the winter. You still see a lot of variability in the summer peak, though. So again, just like a real plug for the need for including enough climate data to tackle the questions that the power system is really trying to answer. Also, this is just demand, and as one might expect, demand has implications for what you build on the supply side. So these are sort of the same scenarios, 2020 and then 2050 with and without climate change considered. You're building a really different mix of generation, right? You're building, your peak is lower, your maximum peak is lower because of climate change in Texas because of the reduction in winter heating needs. And so you're building less gas, you have more wind, more solar, more batteries, but it has huge implications. How you include climate data and what sort of climate data you include has real implications for how a utility company would plan their grid and how they would spend literal billions of dollars to build out our supply to meet future demands. Okay, so diving more into climate data, which is hopefully more in your area of expertise. Climate data is a large space, as you all know, right? So we have this natural variability that I just talked about. I just showed the impact of the climate warming signal, right? The different scenario projections that we might want to consider. And then there's also a ton of uncertainty that makes utility companies and decision makers actually across the board really nervous. And so we take this climate data. We also have a whole suite of power system models, right? From planning models to more sort of simulation and evaluation type models that might take a typical meteorological year. Maybe some folks are trying to be better about climate change and taking like single extreme event snapshots, right? Running a simulation through a 5-day heat wave or something like that. And then there are other planning tools that look at just physical stability of the physics of the system that would take an hourly snapshot and really dive into the dynamics of what's happening with the power flow. You cannot represent climate change with a single year or a single event or a single hour, obviously. And so if we try to be smarter about throwing more data at this problem, it gets more computationally complex. And so we really need to choose the right types of years, the right types of extreme events, the right hourly snapshots, and perhaps have some iteration across these tools to make sure that we're not missing anything in considering climate risk. An example of that is thinking about extreme events. So if we think about a 1 in 50 year heat wave in Texas, it matters how you define it, right? This should not be a surprise. You can get drastically different events if you're looking at a 10-day average, a 3-day average, if you're focusing on a smaller region of a city or a county versus the whole state overall. And your grid will respond really differently, as I'll quickly breeze through here. So this is showing like a really rough measure of grid stress because of heat. So heat on transmission lines, but also wind helps dissipate that heat. So there's like this complex interaction among multiple variables, as we've heard in some of the talks on wet bulb globe temperature, right? There are these complex interactions of the wind helps cool things, and so maybe actually it's not the hottest period if the wind's blowing, it's a warm period when the wind's not blowing. Also, when the wind's not blowing, you don't have wind production from wind turbines, and so like that adds to grid stress. But anyway, there's a lot that matters, and just looking at a single variable is not sufficient to understand how to plan for climate change and for extreme events that are likely to stress the grid. And so, what are we doing about it? Real quickly, within Climate Ready, we have developed some approaches to try to screen a vast amount of climate data. So taking hourly future projections, we've got a method to try to create that because hourly data is really important to get diurnal effects of load and wind and solar. And running it through like these really approximate models that allow us to get conservative estimates of when things might be stressful, and then feed those periods of time into much more detailed planning models. So what this can look like, it's a hypothetical representation of sort of weather in the top left. If we just have a whole bunch of weather years, the risk screening tool can point to like, hey, these are the periods you really might want to pay attention to. Just as a little teaser, turns out it's mostly summer periods. They do reduce over time. If you're looking at 2035 versus 2050, it's these hot periods that are really starting to be the most impactful for the ability of the system to meet loads. And then we can identify those events. We can cluster them and try to pull out important characteristics of these events and choose years that might have the right types of extremes if we want to evaluate an entire year, or choose single snapshot events or single snapshot hours. We can plug these into planning models and look at sort of a trade-off of resilience, right? Of resilience. So how resilient we want to be comes with a little bit of an additional cost. But it turns out it's not that much more, right? Percentage-wise, like 3-4% more than a baseline system to be a lot more resilient. And I'm going to skip this slide, but I will end here, where if you plan with resilience, so without Diving into the details, the baseline case is we're not considering climate change in building a future power grid. The LLT0 and LLT10 represent two different levels of resilience, with the 0% being the most resilient, meaning your loss load tolerance is 0%. We need to serve all of the load. We have these orders of magnitude differences in terms of the ability of the system to meet load across a suite of really common resource adequacy metrics for the system. Just to quickly visualize what that looks like for just a single example heat event, you simply do not have enough supply to meet the load if you don't plan for climate change from the start. I will skip this and end with a really quick plug for local folks. Climate Ready is having an event that's open to the public in New York at this wonderful hotel at JFK Airport in August. Let me know if you're interested. Thanks.
All right, we got to go on to the next speaker, but thank you for the really nice talk. The next person is Zhang.
It's great to be here. So I'm here to share a conceptual study on new type of compound energy risk. I really appreciate the previous speaker. She covered lots of like the introductory stuff in my talk, so I can go very quickly now. So, okay, the green button. Okay, yeah, great. So, as an introduction, the climate energy issues are intertwined issues. So, we need reliable energy to mitigate impacts of climate warming, as we have learned in the last 2 days. Then, on the other hand, we need clean energy to curb greenhouse gas emissions. Otherwise, the temperature will just keep rising. Would make it harder and harder to adapt to these heat extremes. So luckily, our world is making progress. We are adding lots of renewable energy to our electricity system. So in some areas, like the wind energy has accounted close to 50% of the total electricity use. So it's making fast progress. On the other hand, the renewable energy can be very sensitive to weather climate variations. So this makes our electricity system more sensitive to these long-term trends. So one way to think about the future compound risk is to go through the demand and supply of electricity. So on the demand side, we care about the cooling demand, industry use, etc. On the supply side, we have fossil fuels, wind, solar, this renewable energy. So it's critical to maintain this demand-supply balance. So here I'm highlighting this scenario with extreme heat. So if we have such event, we would have very high cooling demand. Assuming the supply does not change much, then we would likely have some imbalance problem. So what follows will be a price spike. So this could lead to energy poverty problems. If things get worse, we could have blackout events. Then there could be grave consequences for the public health. So lots of people have been studying these issues from climate energy finance modeling perspectives. But there's a distinct disconnect among these communities. People mostly look at these problems in their own subfields. So, for example, the wind energy is very sensitive to weather perturbations. There have been studies looking at how climate warming might affect the future wind energy output. Most studies just end there. They do not look at the energy system or the financial implications of such projected changes. So the question is, well, like how will these project changes affect the energy security and the investment? More specifically, can we quantify the threat for the energy demand-supply imbalance? So in this study, we have a long story short version. If in the future we would see amplified summer land warming, which may reduce the wind power output. So this would affect the cost competitiveness of this wind energy and also threaten the energy security. So this is a headline story. So how did I arrive at this conclusion? Well, we look at past analysis dataset and the future climate simulations. So for the climate simulations, we use large ensemble simulations from 3 modeling centers. So this involves over 150 scenarios. So using this data, we conduct physical analysis, such as the time of emergence physical mechanism studies. Then we also conduct a analysis from the finance and energy perspectives. So for this study, we examined 4 topics. So here we only have time to go through 2 of them. The first one is the projections of the surface temperature and wind speed. The second one is the compounding risk for the summer energy shortage. So the slides is messed up here. Actually, this study mostly rely on this UNCA large ensemble simulation. We also examined other other climate simulations. So let's go through some of the results. So in this plot, we have the wind farms being represented with red dots. You can see most of the existing wind farms were built in North America, Europe, Asia. The color shading represents the wind climatology from the ERI5 data. We have relatively high wind speed over the ocean and the mid-latitude storm track. So now let's look at the changes projected by the large ensemble model. So in this plot, we are looking at the northern hemisphere of winter, and the contours represent the temperature change. You see very high warming, very strong warming in the polar region. This is the polar application studied by many other people. Then the color shading representing the relative change of the wind speed. So you see some of the changes across the mid-latitudes, low latitudes, but general in the northern hemisphere, the changes tend to be very small during the winter time. So how about the summertime? Well, now we have some interesting changes in the wind speed. So you have widespread color, bluish color shading indicating loss of the wind power output. At the same time, you also have amplified warming over the land. So this is an interesting combination. You have enhanced warming that may increase the demand of the cooling. On the other hand, you have reduction of wind speed that may reduce your energy supply. So in the study, we look at all the climate simulations, try to dig into the physical mechanisms. But in the end, we care about the real-world implications. Why should we care about these projected changes? I'll give you one example in the next few slides. So broadly speaking, we may experience significant wind changes before 2050. So these changes can be just a few percent, but remember the energy output is proportional to the cube of the wind speed. So even if you have like 10% wind reduction, the energy loss can be as much as 30% or so. So considering we are also going to experience strong warming, the question becomes, well, how may these changes affect the energy investment and security? For the energy security, we can try to estimate the cooling demand using some metrics. Here I'm just using a very simple metric, the cooling degree days. So the definition is straightforward. You have a reference temperature of the daily average. Then you calculate the daily average temperature with the difference between the daily average temperature and the reference temperature. So if your temperature is above the reference temperature, you turn on the AC, you have cooling demand. So this is a nonlinear relationship. We can apply this metric to the model simulation results. So this is a CESM large ensemble simulation. As you might expect, we have the highest cooling demand in the low latitudes. The mid latitude will have some low values. But if you look at the future changes, you see large relative changes in the mid latitude region. In many parts of the mid latitudes, you see increase of 100%. That includes the a lot of regions in North America, Europe. So this is a big change in the cooling demand. So in the next slides, we are going to look at 3 regions in the world: Central North America, West Europe, and East Asia. So we want to look at the changes of the cooling demand and the changes of the wind energy output. So we first look at the Central North America. In this plot, we have several curves. The red curves representing the cooling demand. We have three scenarios. The first one is the reference climatology. Second one is the near future. Last one is far future. You can see the cooling demand is increased. It becomes more intense during the peak season. It also expands significantly, becomes longer. Then the blue lines indicate a potential reduction in the wind power output. So the dark blue line represents a projection by a CESM large ensemble near the end of the century. So you see general reduction up to about 30% at the end of the century. Has some seasonal variations, but the biggest reduction occurs around June. The light blue line indicates the results from the other model simulations. You see the pattern looks different, and the reduction is more amplified during the summer season. Now we look at the other regions. So in Europe and Asia, we see similar patterns of the cooling demand increase, but for the wind generation, in some other regions, we see a more amplified reduction during the summertime. This is especially the case for the European regions. So this is a common pattern in the northern hemisphere, middle latitudes. So in the end, we will likely have a big imbalance between the energy demand and the generation of the wind power. So I would argue this is a high-stake compound risk. So for now, we already know that the electricity grid is already in trouble in North America. This is some information from a recent report. So for the summer peak electricity demand, it's going to increase. We will also have some generation resource increase, but the increase is not as fast as the demand increase. In some of the specific regions, such as the Central North America, we could face some significant shortage in about 4 years. So that's something very pressing. So the question is whether the utility planners have considered the long-term compounding risk related to the wind energy. I don't know the answer for sure. Some of the audience probably know that. So to sum up this talk, we would see amplified summer warming. This would reduce the wind energy output. It could affect the cost competitiveness and the energy security. So if you are interested in the details of the findings, you can look up the preprint using the QR code. I will just go through the key findings very quickly. So for the projections and surface projection of future, we would see a reduction of the wind speed in the middle latitude accompanied by the land warming. Then the significant changes might emerge around 2050. So this is the most amplified in the summertime. Then for the reduction, the reduction of the wind speed would affect the cost competitiveness of the wind energy projects. The good news is that even in the most adverse scenario, the strongest warming, the wind energy would still remain more cost competitive relative to the fossil fuels. So just based on the economic arguments alone, the wind energy development will keep going. Regarding that, if we have more wind energy installed on the electricity grid, we probably should care more about the compounding risk as discussed earlier, especially for the middle latitude hotspots. So personally, I'm confident about the future development of wind energy. This recommendation is just to diversify the energy portfolio, adding more complementary energy sources like solar energy. That's all I have. Thank you.
All right, one quick question and one quick answer.
Thank you for a very nice talk. I just have a very naive question maybe. So here just consider the wind energy, but as I understand, when there is a high temperature, maybe there will be more radiation. And then how about solar energy?
Yeah, that's a good idea. So that's essentially the recommendation here. If you add more solar energy, you probably would largely mitigate the problems highlighted by the solar related to the wind energy. So in some parts of the world, people are installing lots of wind energy alone. But in some other parts, it will be a better idea to install both wind and solar so that you will not run into the problems during the episodes of wind droughts.
Okay, thank you.
Yeah, great. Thank you.
All right. We're on for our last speaker of the day, James Doss-Gollin. Bring us home.
Hi, everyone. James Doss-Gollin. I'm an assistant professor in civil and environmental engineering at Rice University in Houston. Have a little bit of an interdisciplinary background. Maybe the subfield that I'm closest to would be like a stochastic hydrology, so very much a use-inspired approach to working with climate data, trying to bridge between engineering and physical science. I think we've heard a lot from the physical science side of things at this workshop so far, so I'm going to try to give a little bit of an overview of the energy sector. I'll try not to be redundant because Andrea said a lot of these things really well. So I was in the UK a couple weeks ago, and I was on a train and saw this newspaper lying on the seat. And it started to make me laugh because it was cold enough. I could just about bear to take my sweatshirt off by 10 in the morning, but it didn't feel hot to me. That being said, as we've heard in the breakout sessions, we've heard in this session, you've got places where people not only don't have air conditioning, they don't have fans, they have houses that are designed to retain heat. And so even with these temperatures that to me didn't feel hot at all, people can be very vulnerable. And so there may be physiological adaptation, there may be behavioral practices that are relevant, but what I really wanted to highlight is that infrastructure is absolutely essential for modulating those impacts between extreme heat and people. This is both a challenge and an opportunity because we get to build the infrastructure that we want. Another sort of personal anecdote around this, so Hurricane Beryl made landfall in Texas, not too far from where I live and work, a couple days ago. It made landfall as a Category 1 hurricane. So what we saw, we've got this there we go. We've got this hurricane, the wind fields from it knocked out. We saw trees that were down. We saw power lines that were down. Lots of direct impacts on the transmission and distribution system. And so this map here at the bottom is showing number of customers without power. This screenshot was taken about 24 hours after landfall, and in Harris County, where most of Houston is, about 60% of customers were without power. There's still, I believe, 1 million or so customers several days later. And this is all happening during a heat index of around 105 degrees Fahrenheit. So people are experiencing extreme heat because the infrastructure system is not protecting them. I'll go very quickly here because Andrea spoke to a lot of these sort of other heat impacts on energy systems. So from day to day, temperature is the main thing that drives variability of energy demand. So what we see is these two different colors. They're just every day, every dot is one day during a summer. And so we see when it's hotter out, there's more demand for heating. This is only looking at the Texas grid. But the other thing I'll highlight, and we'll come back to this in a little bit, is that when you jump from 1996, which is this green line, to 2020, which is this yellow line, you see a huge shift. So that speaks to the sort of speed with which our system is changing. And again, that's something I'll talk about more in a second. As Andrea said, when it gets hotter and demand goes up, that changes the demand that changes electricity demand. So this is something called a dispatch curve. Basically, at every time step, you have all your utilities bid, or all your generators bid how much, sort of at what price they would switch on, and you line them up from cheapest to most expensive, and then that sets let's say your demand is here, your price will be here. Let's say your demand is here, your price will be there, more or less, with some additional constraints built on. The main point is that as demand goes up, not only is it more expensive, but typically These will be like your renewables, nuclear, natural gas, and coal. So not only is it more expensive, but you also have dirtier sources that you're switching on. There's the transmission and distribution impacts, generation, so heat directly stresses infrastructure components. And then you get some of these other sort of planning challenges at different time scales. So for example, you might need to keep all your generation on in the winter because you might get a cold snap. You need to keep it on in the summer because it's hot and people have air conditioning. As the summer gets longer due to climate change, that sort of shoulder season in the fall and spring when you can do maintenance shrinks, and that's a really big challenge for operators. The sort of next thing, as we sort of pivot to talking about potential solutions and ways that we can increase the resilience of our energy systems to heat, it's really important to keep in mind that our energy system is changing really fast. So there's lots of published research where people are isolating like the effect of 2100 weather on the grid, but the grid is changing very, very fast. 2100 weather is not going to experience the current grid. So I think we should be skeptical of this claim, but there's been suggestions that the electricity demand in Texas could double in 6 years. I think that's extreme, but we're seeing electrification of building heating. We're seeing electrification of transport. We're seeing data centers going up, population growth and demographic change, people buying air conditioning, all these things. And these, to different extents, these are happening all around the world. So demand for electricity is going up rapidly. We're also seeing rapid rollout of renewable generation, especially. So in Texas, there was just a couple of weeks ago a peak of about 38 gigawatts, which was over half of renewable generation. Solar's gone from basically nothing to pretty huge in a very short time span. That's going to continue. And as Doug here points out, transmission and distribution is increasingly a bottleneck. So there's lots of ideas about ways that we might be able to build energy systems that are more, that do better and help people manage extreme heat more effectively. Everything from building new generation and distribution and storage, especially distributed, but also just sort of grid scale. We can harden specific components, so that's making sure that when it's windy or when it's hot out, that our specific, all utility poles don't fall down, every transformer is working. There's demand response can be part of the solution, long distance transmission so you can generate electricity in one place and sell it in another place, education and workforce needs, all kinds of things. I'm not, there's more than anyone could go into. These all happen on different timescales. We often talk as though we need to know exactly what infrastructure we'll build for 2100, and we need to start building that today. I was thinking with this sketch about flooding, but I think the point that as you get farther and farther into the future, the uncertainties that you're grappling with get bigger and deeper very quickly. If you're talking about energy systems in 2100, it's not just how much climate change are you facing, but you also have questions about what's the price of solar panels and batteries? Where are people living in the world? What kinds of houses are they living in? All of these things are really important. And so as we're trying to build resilient energy systems, the focus needs to shift a little bit from today building the infrastructure that we need forever to thinking about what are actions we can take today that meet the very real-term challenges we have. Like our infrastructure is already in many places failing. At the same time, we don't want to build something that we're then going to need to repair and replace, dig up things that are buried underground in 10 years because they're inadequate. I have a little bit of actual research that I'll talk about. So this is actually similar to one of the plots that Andrea showed as well. This is looking at average, basically a cooling degree days like metric, so like we saw in the previous slide, for 3 different grids. So this is Florida, the Midwest, and California, and this is just based on reanalysis data, how these have changed over time. So the story for all of these is pretty simple, that demand for cooling has gone up, demand for heating has gone down. But that's not really the whole story. What we see when we look at the peaks, which again, the peaks are, you have to design your system to tolerate the peaks. The peaks are, this is very much not the story. So even in Florida, which is a place that, is much, we think of it as being a hot place, This is similar to Texas. We see similar things there. Those like rare winter peaks generate potentially more heating degree peaks than you have cooling degree peaks in the summertime. There's not a one-to-one relationship between heating degree days and cooling degree days in demand, but it means you need to be designing your system for those rare peaks. Similarly, in California, we see that there's actually huge variability from year to year of both the summertime and the wintertime peaks. So making sure that we have this kind of variability in our energy systems and energy resilience models is essential. So I wanted to end by thinking a little bit about where climate science can be useful in this space. So we've heard a lot of people talking about the Pacific Northwest heat wave from a couple of years ago, right? And we've got this, it looks like a huge anomaly if you only look at data from that, local data and observations. And engineers, we are super, super primed to use observations because it feels more objective and we have more precedent using observations in a particular place than using models, because everyone understands models are imperfect. They're not completely representing the real world. The problem is that if we only use observations from the past, we're going to be malinformed. So one of the things where climate science can really help is just helping to imagine what hazards might be. So this is again from this work looking at demand in the Texas grid. This was just taking, I believe it was CSM simulations from the relevant decade and looking at I think it's a 49-member ensemble. And you can start to capture the variability, and it turns out that a lot of the peaks that we've experienced in the past are in there. There's obviously additional ways to try to do this, but the point being that using models, using climate science to help understand, these aren't distant future risks, these are helping people to understand the risks that we face right now, because the sort of empirical observation-only approaches that we've been comfortable with aren't adequate. So to wrap up, again, we have inadequate understanding of both the likelihood and also especially the impacts of local extreme temperature on energy systems. As talking about with the tropical cyclone, the impacts of heat on people are modulated by infrastructure, so making sure that if we're trying to study impacts on people, we're including infrastructure in those models. And finally, that we need to build energy system resilience into rapid infrastructure evolution. So instead of ending just with those sort of observations about the world, I wanted to end with two ideas about how we can do better. So the first is using, whether these are large ensemble simulations or other approaches, we can combine, I think there's lots of opportunities here to combine machine learning and AI, weather, infrastructure, and social models to understand our sort of immediate near-term risks. And then the long-term planning is really hard. These long-term capacity expansion models are already computationally really challenging, including uncertainty from multiple sectors and in weather variability is really difficult. But trying to come up with clever ways to do that as best we can is going to be incredibly valuable as we try to figure out, of all the near-term actions we could take that meet our near-term needs, which of them are also consistent with our long-term goals. So I'll plug, we talked about some of this in a review paper that came out about a year ago, and we've got a website to learn more. We do a lot of things related to flooding as well, but really glad to be here. So thanks very much.
All right, we got a lot of people thirsty for coffee, so one quick question, one quick answer.
Hi, I'm Lo from Princeton. Very nice talk. And so just wondering, you mentioned the distributed generations would be a solution. I mean, solar could be a very good. But I mean, do you think the distributed solar will be better than utility scale solar? Because there's really high cost for distributed solar in the United States compared to utility scale, and it may compete with the utility scale solar.
Yeah, that's a great question. I certainly don't think that distributed generation is a silver bullet that's going to solve all problems everywhere. A lot of the costs of utility scale solar in the U.S. specifically seem to be related to getting someone to do the electrical work on your house, getting people who can do the roofing, doing permitting and some of that. So there certainly seems like there, theoretically, from an engineering and science point of view, those costs could come down and it can contribute. Is it going to compete with grid scale solar? I personally, I'm not sure exactly how that would happen, just because there's such, in places where demand is growing so rapidly, it seems like a more and all of the above. I think the real value for distributed generation, it's less cost effective on a sort of per unit basis than grid scale generation. But if your sort of hard constraint is the transmission and distribution system, then certainly if you're using it all within a particular building and not sending it back onto the grid, then you're reducing you're sort of being able to have more total electricity use without needing to upgrade the transmission distribution grid. So
Thanks.
All right. Well, thank you again to all the speakers. This was a fantastic session.